One other thing that we need to consider, especially when we talk about ionic compounds, is the role of what's called polyatomic ions. It actually nicely sounds exactly like what it is. It's many atoms with a charge, right? And that's kind of interpreting poly for many, atomic for atoms. And then ion is what you call an element with a charge. So polyatomic ions are really no different than just big honking messes of the ions that we talked about before. So for instance, let's just pick out, say, bromine, right? Well, bromine is not polyatomic. Bromine is just its own thing, right? We could put in a Br minus here, put a jacket around it, put a 1 minus charge on it, and it turns out that's just what's called a simple anion, right? So a simple anion. Sometimes you'll see the word simple attached to things that are not complex or not polyatomic, right? There may be a bazillion bromines in our ionic formula for something, but the fact is that bromine is the thing that is charged. Well, it turns out polyatomic ions are actually this big group of covalently bonded nonmetals that have some sort of excess or deficiency of electrons, which means that it has overall a charge, right? Because we've talked about electrons being the thing that's moved around to determine whether or not something has a charge. So what I'm going to give you is, first of all, a list of polyatomic ions, which I highly encourage you to use. I'll just kind of draw one that is a polyatomic ion with a 1 minus charge. This is the Lewis structure of this thing. So notice I've got huge jackets, but the important thing is that that thing overall has a 1 minus charge. That is, in a sense, functionally no different than a bromine. This whole entire thing is just going to act like a single atom with an extra electron. It just so happens that this thing, right, kind of gets carried around as a group, right? That whole idea of a molecule. Technically, these polyatomic ions are charged molecules that just kind of all float around together. But what can happen is that this thing can be involved in some sort of ionic compound. This thing is called either complex anion, or a polyatomic anion. So we should probably talk about, how do we do a question that asks us to do a formula that involves some sort of polyatomic? Before I go, I forgot. When you look these things up, right, this thing, you'll notice, has 1 nitrogen and 3 oxygens. So you might see it symbolized like this, right? This is the Lewis structure, which we'll talk about eventually. And this is just how you would draw it as kind of a condensed representation. This guy is called a nitrate. Probably can't read that, I apologize, but hopefully you can look it up on the list that I gave you and see that thing's called a nitrate. All of these things have names. A really common thing that you'd have to do in a 200 level class is to kind of memorize many of these really important ones. I'm not going to have you do that. It's a total waste of time in my opinion. If you ever have a question, just look it up. So one thing I did want to mention though is that if this thing is a nitrate, it turns out there's also a nitrite, which only has 2 oxygens and a 1 minus charge. So just be kind of careful, especially when we get to that compound naming. You'll get a little bit more experience with this in the lab. Just be careful you recognize that there's a lot of difference between an ate, an ite, and an ide, right? A nitride would be just nitrogen with its 3 minus charge. A nitrate is a nitrogen, 3 oxygens, and a 1 minus charge. A nitrite is a nitrogen, 2 oxygens, and a 1 minus charge. You gotta thank chemists for coming up with these god-awful names. Okay, so let's say we encounter something that involves a metal, which is good. We know that it's got to be ionic in a compound. And we want to combine that with one of our polyatomics, the thing that we just saw called nitrate. Well, it turns out all you need to do is look at your polyatomic ion list to figure out what the charge on that thing is, which turns out to be an NO3 1 minus, or by the way, you can just call it NO3 minus. Sometimes the 1 is left off. And then you look at magnesium and figure out what the charge on magnesium is. Being an alkaline earth metal, it is actually 2 plus. And so now we're ready for our crossy trick, but we got to be a little careful about something. When we figure out the formula here, you'll notice that when we write it, right, the 1 is left off, so I'm going to leave that off. But the problem is that if I just do this, right, if I just put the 2 down there next to this, you're kind of like, well, what the heck is that, right? Is it telling me that I need 32 oxygens and 1 nitrogen? No. What it's telling me is that I need to take this entire thing, that entire NO3, and double it, right? I need 2 of them, 2 1 minus charges, in other words. And so what we see here is the use of parentheses. If you see parentheses, it's almost always the case that you involve some sort of polyatomic ion. And by the way, if there was only 1 there, you would leave the parentheses off. So for instance, like if we did the formula for sodium nitrate, that thing would look like that, right? Just 1 sodium, 1 NO3, you leave the parentheses off. Turns out that this big giant group of nonmetals is once again just a nitrate. So don't get confused if you see parentheses or if you see something that, for instance, isn't on the periodic table. You're like, I don't see any nitrates on the periodic table. Yeah, that's because it's from the polyatomic ion list. So just kind of be aware of that. There's one other thing that we got to be real careful about, which I'll mention in the next video, and then I'll shut up for at least today. Turns out there is a polyatomic ion out there that screws with us a little bit. And it turns out that that polyatomic ion looks like this. This sucker is called ammonium. Ammonium is a really common polyatomic ion, especially in like living systems and things like that. That's what's, a big component of urine and stuff like that. Gross. Biology's so gross and icky. But one of the things that kind of screws things up is that, again, that positive charge, right, it just takes the place of kind of a normal positively charged element. So let's say this thing could take the place of, let's say, a sodium plus in a compound. The thing that screws us up is that you'll notice that nitrogen and hydrogen are all nonmetals. Remember, hydrogen is still a nonmetal, even though we put it on the left side of the table. Hydrogen screws everything up. But anyway, so hydrogen and nitrogen, right, they're both nonmetals. So what happens is that we really, in terms of discovering whether or not we're talking about an ionic compound or a covalent compound, I told you that you should ask, is there a metal present? If there is a metal present, it is definitely going to be an ionic compound, right? And we use all the ionic rules. We really have to add this to that list, right? We should really be asking not just is everything, or does it contain a metal, but we should ask, does it contain a metal or ammonium, right? Or NH4 plus, right? It's important that you recognize that things that involve ammonium are also ionic compounds, even though when you look at them, they involve only nonmetals, right? It's kind of that weird exception, but it's just such a common molecule that we have to be aware of it. So what I'll do is I'll just kind of show you a normal type of formula without a polyatomic ion, and then I'll show you what the formula with ammonium might look like, and I think then we'll be good to go, and I promise I'll shut up after that. Okay, so we've got 2 examples of compound names. One is cesium phosphide, one is ammonium phosphide. We're going to apply the rules that we know for figuring out the formula for an ionic compound because we know they're both ionic compounds. We asked, is there a metal present? And we'd say yes, cesium is a metal. We ask, is there a metal present? And we say no, but wait, there's an ammonium, so therefore it's an ionic as well. So how do we handle this? Well, Cesium phosphide, you're going to go through the same, oh, what the heck is that? You're going to go through the same exact process that we've done a billion times. A billion by what I mean is 3. So we do a cesium and a phosphorus. We figure out what the charge is. I'm sorry I'm going a little fast here, but I don't want to waste any more of your time. We've got a 1 plus charge and a 3 minus charge. We do a Crossy trick. We end up with a formula that takes 3 cesiums and 1 phosphorus. And then we look at ammonium phosphide. This one takes a little bit more effort because you have to look up ammonium on the list or remember what it is. This is the one that probably is more helpful to remember. And then we've got our 3 minus phosphorus. And we do our Crossy trick once again. And what we end up with for a formula for ammonium phosphide is our ammonium taken 3 times and a phosphorus, right? We know that anytime we've got more than 1 polyatomic, we need to include parentheses. So you'll notice here the 2 appearances of this particular ionic compound.